We've talked a little bit about arc length here, and arc length is going to be useful for when you're doing linear and angular speeds. The biggest thing you have to remember, and continually people forget, is that your theta must be in radians, not in degrees. Okay, people always forget this, no matter how much I might highlight it, or no matter how much I might maybe underline it. People always forget theta has to be in radians. Okay, you can't leave it in degrees. If you leave it in degrees, then you're not going to be able to multiply. You can't multiply like a length times a degree. So here's a couple of formulas for linear speed and angular speed, and I will give these to you for your quizzes and tests. If s is the length of the arc, okay, traveled in time t, then linear speed is s over t, your arc length divided by your time. Okay, when we're talking about linear speed, that measures how fast a particle moves. So basically, if you think about like the tip of a blade of a helicopter, then if you're thinking about how fast each blade rotates, well, you're going to find out by taking the end point of that blade, and you're going to multiply the arc length by the time. So if you have your arc length here, you have an s over t. Well, we also know that s is equal to r theta, all divided by t. And another way you could look at this would also be if you separate the r from the theta and the t. And this is going to be important here in a moment, and I'll show you why. So these are three different ways you could represent linear speed. Angular speed, that is going to be how fast the angle changes. So angular speed is how fast. Okay, angle, so it has to do something with angles. Linear, that's how something goes in a circle here. So if you have your angular speed, here your angular speed is just your central angle. So whatever the rotations are, however big the angle is from the middle, divided by your time. Now notice this theta over t, your angular speed, it's right here also. So basically for your linear speed, another way to figure out your linear speed would just be to take your radius times your angular speed. Okay, so your linear speed can actually be found pretty quick if you already know your angular speed. So let's look at example 6. Here we're talking about the second hand of a clock is 8 centimeters long. Find the linear speed of the tip of the second hand as it passes around the clock face. So what we're going to do is we have to find the linear speed. So your linear speed, we're going to use s over t. S over t, that's the same thing as saying radius times your theta of your time. Now in this case, we have your r, your radius, is equal to 8 centimeters. Your theta, this is not as evident, and your time is not as obvious either, so we have to think here for a minute. Theta, we want to find how long it takes for the second hand to pass around the clock face. So if you're going around a circle, how many radians is that? Remember, this has to be in radians. Also, we're not talking, yeah, it goes around 360 degrees, but if you go around a circle in 360 degrees, that's also equal to a 2 pi radians. Now your time, well, if we're talking about a second hand, your second hand goes around a clock in 60, or a total of 60 seconds per minute. So 60 seconds is the time it takes to get around the clock. So if we plug these values into our equation, we're going to take our 8 centimeters times our 2 pi radians, and we're going to divide that by 60 seconds, which ends up, and if you plug this into your calculator, that ends up being about 0.8377 centimeters. Ooh, that's kind of ugly. So that's centimeters per second. And then that's going to be your solution. Okay, so what you need to figure out is you need to figure out what equation, what formula you're going to use, and then you need to figure out also what your radius, your theta, and your time is going to be. So there's the easy example.